Hi everyone, my name is Bora and I'm here today to talk about subject-specific models for predicting human locomotor response to ankle foot orthoses. And my collaborators are Michael Rosenberg, Ramona Yamagami, Professor Kat Steele, Professor Sam Burden. So for those of you who aren't familiar, ankle foot orthoses, or AFOs, are used to assist those with movement disorders, such as cerebral palsy and stroke survivors. Currently, spring stiffnesses for passive AFOs are chosen by clinicians through trial and error. The goal of our project in general is to improve clinical outcomes. We hope to assist clinicians in picking spring stiffnesses. To facilitate the development of predictive models that will let us choose spring stiffnesses, we decided to run an experiment. We took 12 healthy participants and had them walk at a constant speed on a treadmill. We subjected them to 4 bilateral AFO stiffnesses, one of which was control, so no spring. We measured marker kinematics and electromyography, or EMG. And the goal of our pilot study was to develop, assess, and survey methods with an aim to eventually translate our methods to participants with motor impairments. The first step was, since the participants are engaging in a rhythmic task, was to estimate their phase. So we estimated the phase at all measurements using the phasor algorithm, and this will be built upon with our later models. The input-output structure of our models is we take a phase, or we take a state at some phase phi, so that's x, and we try to predict x hat at some phase phi plus theta, where theta is the phase look ahead. We also wanted to incorporate the influence of the AFO. We treat the AFO as an external perturbation, and we allow ourselves access to future estimates of the torque applied by the AFO. So even though we're predicting from phi, we're allowing us access up to phi plus theta. And so now we're going to look at 3 models. And so the first model is kind of the base case, and it's the phase average model, which is purely a nonlinear function of phase. It's relatively simple and specific to the task of rhythmic locomotion. All you have to do is provide it a phase, and you get the phase mean. And this means we chose a truncated Fourier series to represent it. Next model is the linear phase varying model. And so that means it's non-linearly a function of phase and linearly function of state. The LPV model builds upon the phase average model, but it also builds in our understanding that we think individuals correct for perturbations from a desired rhythmic behavior. Or if you look from the theoretical perspective, that trajectories will exponentially converge for a stable limit cycle. And this motivates increasing the complexity of the model as we're attempting to model the stabilizing dynamics. And lastly is the nonlinear phase varying model, which in this case is the feed-forward neural network. Neural networks in general are state-of-the-art in a lot of domains, but to ensure a relative comparison, we pick the LPV model, or we pick the feed-forward neural network versus the recurrent neural network to ensure the same input-output pairing. And so these are our results. So on the y-axis, we have the relative remaining variance. So this is the variance of the residuals over the variance of the data. And as you can imagine, a 0 means you're doing a perfect job of predicting, and a RV of 1 or greater means you're not predicting anything. And as you can see for the first 3, which are joint angles, ankle, knee, hip, we're doing a pretty good job across the board. Generally, as we increase the complexity of the model, we're achieving slightly better results. These results are the distributions of RV values for each individual. And so as you can see for individuals in general, we're doing really well for some individuals and quite poorly for others. And then the 3 outcomes on the right are the EMG measurements. In general, we're not doing as good of a job in EMG. Oh wow, that's really fast. Okay. Yeah, so I'd like to thank my funding sources and any questions?